We'll actually discuss about some topic related to the force and also force itself, and we'll also cover some circular motions like kind of moment of inertia, radius of gyration, and then we'll think about angular momentum. We'll also cover linear momentum, frictional force, like impulse force, tension force. So these are all topics related to the force. So let us first come to know about the force. First force. So force is vector quantity, we all know, and the definition of force is with simple word like you say, for example, force is anything that can accelerate an object. For example, this is an object, and if we apply force on it, what will happen? This force will just accelerate. So force can change the velocity of an object. So there are some other character of force that we can add. First, and the force has a direction because it's a vector quantity, so obviously it will have direction. So the force always works in a certain direction. For example, our weight that works downward always, right? So again, so it has direction, right? So you can write it has direction. That is a property of force. And then number two is force can deform an object. Like there are some flexible objects around, and then if we apply force to that, we'll see these objects started deforming. So if you'd like to actually change the shape of an object, you have to apply force. So it can deform an object, right? Object. So that's a property of force. And then force works in pair. Like if we apply a force to an object, there will always be a reaction force to that, and action and reaction works simultaneously. So when you write, even as I'm standing here, that means what? I am applying a force equal to my weight to the floor, and floor is also at the same time reacting it with the reaction force equal to my applied force. That's why I'm here. If floor would have had more forces in reaction, then I would have gone up, right? So or if my force is more, then I might get down. So actually it's equal. And then so force works in pair, right? Force works in pair. Okay. And that is some of them. Force can accelerate an object. It can change the velocity of an object. That's what we have already talked about. So, and now there are some kind of fundamental force that we see in our nature. So what are those forces? Let's talk about fundamental force. So fundamental force, the first one that comes into play is the gravitational force, right? So gravitational force. So what is that actually? Gravitational force is like every object in the universe attracts each other. Very simple statement. And actually it's the mass. So gravitational force actually is based on the mass of an object. The object that has more mass will have more actually attraction force. For example, if an object has got this mass, an object has got that mass. So this one has got more weight, more mass, so it will attract this object more towards it, and this object will actually come to that object. I mean, that object will come to this object. I mean, the object of the less mass will have will start coming to towards the object of more mass. That because the object having more mass will generate more forces. So that's why the gravitational force depends on the mass. So actually if we think about the mass of this object is m1 and this object is m2, and then the distance between them is d. So the gravitational force acting between them is g, is the gravitational constant, and m1 m2 divided by d square. Actually this force depends on the mass of them, right? So if there is more mass, the more force is working between. So this force working within the long distance, that's why we see these stars or all other planets, they are too far away from each other, and but still they are having the gravitational force working between them, right? So now talk about if the mass is too small, like think about molecules or like atoms. For them the force is not actually, I mean this gravitational force is not working much between them. There are other sorts of force, like other forms of force. Those are also fundamental, like electromagnetic force, force between charges. These are working for the tiny particle. These gravitational forces are also working there, but it's not intensity is not that much high compared to the other forces. Now think about electromagnetic force, number 2. Like first one was gravitational force, and the second one is electromagnetic force. Electromagnetic electromagnetic force. Okay, electromagnetic force is actually, there are two actually words here, electro and magnetic, right? So there is a you see that there is negative and positive charge, right? So negative charge, positive charge means there are line of force working outward. Positive means outward, charge means force acting. So anywhere, if we call like we call a word in Bangla like police lathi charge koreche. So lathi means there is stick, and charge means the force applied to that. So charge means applying a force. So the charge, that means applying a force, and positive means outward. So like positive charge means applying a force outward again, and this force are actually called electric line of force. This force, the line of force working here, and that is actually electric force. We would say electric force, right? That develops electric field. And the around negative charge means negative means inward. So the line of force will work inward in around negative charge, like this. So it's nothing but like a space where the positive line of the line of force working, acting outward, and the negative is the line of force acting inward. And what happens when these two charges placed side by side? For example, a positive charge when placed beside a negative charge, the line of force, okay, let me have a different ink. So the line of force for positive and negative, they're working in the same direction, and you know force is a vector quantity, and when working the same direction they get added, and these two comes closer. That's what we call attraction. So two opposite charges, that's how attracts each other by the electric means electric line of force. And think about two positive charges, what happened? They are supposed to repel. Why? Let's see. This positive charge, I mean this line of force working outward, right? And for the other charge also, it's the line of force of that charge will work this way. That means the line of force, the direction of line of force is opposite, we see. And that opposite means what? This, if we take it this way, like this positive line of force, I mean this line of force pulling that charge towards that direction, and this force pulling this one towards this direction. If we think it like that, then they will actually get apart, means there is a distance between, they will repel each other, right? So that is how the electric force develops around a charge. Again, there are other thing we call magnetic material, right? So in a piece of magnet there are north pole and south pole, and there is electric line of there is a magnetic line of force that actually travels from the north pole to the south pole, like this. So the direction of the magnetic line of force is from the north pole to the south pole. And now if we place two actually magnet side by side having same pole exposing each other, what will happen? This thing will happen, right? This line of force will work in the opposite. For example, if you would like to see, I can show you. For example, here, see, this line of force is entering here, right, this way. And if you place a south pole here and north pole here, so this line of force will also travel this way. So what will happen if you see the line of force, the direction of line of force for this is coming in this way, and for that this is coming in this way. See the line of force working in the opposite direction, and that makes them repelling. So similar way as this. So that's how the magnetic line of force and electric line of force, they are developing this electromagnetic force. And there is a link between electric and magnetic force. What is that? For example, if this is a wire, right? A piece of wire, and if you allow the electron to flow through this, like this, right? If you allow the electron to flow through that, and the electron has electric line of force around it, and once the electron flows through where there is a magnetic line of force growing outside this way. So that proves that there is a link between magnetic and electric force. That's why electromagnetic force, we name it together, as they have got relation. Now let's learn about the other form of force, which is strong nuclear force. So strong nuclear force. Okay, so what is that? A strong nuclear force, it acts inside the nucleus within a very short distance, I mean within very small place, right? Because nucleus is too small. So you see inside the nucleus there are protons, right? Positively charged particle, like this. So the protons, they repel each other and they stay in a very tiny place, like nucleus, inside nucleus. So you know, we have already seen that the two same charge repels. That means they repel each other, and two tiny particle or two particles that repels each other cannot be together. They will repel and they will get apart. That is supposed to like happen, right? So why they are together? Because there is a force pulling them together, and that force we call strong nuclear force. This force is very strong because this is working in very short range area. You see the force is inversely proportional to the distance, right? Square of the distance, and that's what makes them like, you know, as they are very much closer, so their nature is very strong. So that's why you know, the force that is pulling the protons of the nucleus together is strong nuclear force, and this is the strongest force of all the fundamental force. And think about weak nuclear force. Weak nuclear force. Okay, what is that? Weak nuclear force, inside it's also working inside the nucleus, and there are some particles like alpha particles, beta particles, neutrino, antineutrino. Between them there are some very weak force working, and that is weak nuclear force. Nothing more you know, is special about it. It is just very weak. So you know, the strongest force is the strong nuclear force between them all, and weakest is the gravitational force. That's it. And now let us move to the Newton's law of force. Newton's law of force, Newton developed three laws, and that is so very popular. We all knows that, like we all know that actually, and we practice it in our daily life. Suppose I'm standing here, someone you as well standing, right, walking, everywhere Newton's law is applied, right? Or any object that is in motion or at rest, in a rest, whatever state that be, right? Or some other phenomenon that is actually happening around regarding forces, that are all based on the Newton's law, actually, that can be explained through the Newton's law. Let us see what Newton's first law of Newton. Okay, what is that? Newton, if you see the statement, it's just, if you don't apply force, the state of the object will remain the same. I mean, if the object is at rest, it will always be at rest. If the object is in motion, it will always be in motion. That's what Newton's first law says. Let's say, let us check it. For example, how we know F equal to ma, right? That's what we know. I can show it. We can see it with this. So if you don't apply any force, that means F equal 0. If you don't apply any force, what is happening? Sorry, F is equal 0, because no force is applied. So if F equals 0, so let us see F equal to 0, then ma, right? 0 equal to ma. Now see, between these two parameters, m cannot be 0, because m is the mass of an object. That cannot be 0. If there is an object, there is a mass. So here m is not equal to 0. Then of course a is equal to 0. So what happened? A is equal 0. So we can write a equal v minus u by t. That means final velocity minus initial velocity divided by time equal to 0. So we can write v minus u equal to 0. So here we can conclude it with v equal to u. That means initial velocity and final velocity will remain same. That means there is no change in velocity. That's what you can say, like if an object having a rest, that means velocity is 0, initial velocity is 0. If you do not apply force, no force, the velocity will always remain 0. That means it will always stay steady, stay fixed. It is not going to move, because there will be no change in velocity if you don't apply force. And again, if another object that was, for example, there was initially that was moving with a velocity 5 meters per second, that means this initial velocity will never change if we do not apply any force. That means see, v equal u. So this object is supposed to keep moving with this constant velocity forever. But in reality, we don't see that. We see that if we keep an object moving with a velocity like 5 meters per second, after some times that object seems to be slowing down and like eventually stopped. Why that happens? Because there is force working, which is frictional force. If you can make all this surface frictionless, or there are air drag or whatever, right? If you can like avoid them, you'll see this object will keep moving like that. There is an experiment, we can check it. The Galileo who performed an experiment to check it. Now, what was that? Let's see the Galileo's experiment. You will have some idea about that. Galileo set a inclined surface like that, and the surface was frictionless. It was thought frictionless, right? So a piece of object like, or a ball, you can see a ball, right? So a ball was actually free. The height was h. So that ball that has potential energy mgh by now, right? And if we release the ball from the top of the inclined surface, and that surface is frictionless, of course, and if there's another inclined surface this way, and it reaches to the same height of h, what will happen? This ball will come down here, and all the potential energy in the ball will be converted into kinetic energy, half mv square, right? So it will have velocity right now, and with this velocity, this, as there is no friction, it will start again climbing up, as there is no friction, and it will climb until it reaches to the height, this height. Its velocity becomes its energy becomes mgh again. So its goal is just to reach to the height, but how much? The height it was before. It was before it reaches to the ground. So it will reach here again. And now at another picture, if you keep the first one same, but for second half, if you just flatten the surface like this, if you just reduce some angle, right, this angle was that and this angle, right, so but reach to the same height like this. This time the path is much more, right? It was before it was up to AB. Now the path extends to AC, right? So of course AC is greater than AB. And now what happened? This time again, for this surface, the same ball, when reaching here at the bottom, will start climbing this, and it will keep reaching to the top until it reaches to the A side again, because it's all kinetic energy has to convert to the potential energy. So it will not stop until it reaches to the A height. Once it reaches A side, it will come down again and will come up again, reach A side, again come down. So it will oscillate like this, right, as the surface is frictionless. So if we do one thing more, which is if we flatten it more and more, like we just keep 0-degree angle like this. So we keep it this one. If we decrease the angle downward and we just make a straight line, the surface make flatten fully right now. What happened when the ball reaches down here, and it will start traveling this way to find the height he was before. He will have it was before, and it will again start finding that height. And as the surface is plane and horizontal, it will never be at the like this way, right, inclined. So and until it reaches to the A side, it will keep running. That means what? It will always keep running, because there is no inclined surface. There is no A side. So as there is no A side, it will keep running. So that's what we can have some idea from this, that if there is a frictionless surface, there is no force applied, the velocity will be same. Anyway, so what is the outcome of this first law? So outcomes. So we've got two ideas from the first law. The number one is force. So idea of force develops from the Newton's first law, and the second one is inertia. So we have already talked about the force. The first law, the statement says if no force is applied, the object in rest will always be in rest. That means we find that if we would like to make an object in a state of motion from rest, we have to apply something, and that is the force. So that is how we can get the idea of force from the first law of Newton. And inertia is like laziness. Laziness means what? Laziness is an object which tends to, or which has the tendency to keep its original state, its previous state going. It doesn't like to change its state of motion. So the tendency of keeping the state of motion as before is actually the inertia. And that's how there are two types of inertia we have, and we experience that as well in our daily life. Let's see. For example, inertia of motion. Inertia of motion. What is that actually? Another one is inertia of rest. inertia of rest. Okay, what is that? Inertia of motion first. You know, how do we experience it? For example, when you sit on a bus, or maybe a private car, or a train, whatever, what happens? If the bus suddenly brakes, if the driver applies the brake suddenly, you see, we find our top portion is moving forward, right? Keeping the bottom portion with the seat, just top portion start moving forward. Why that happens? That happens because of the inertia of motion. When okay, let me show you something. When a passenger, that is the seat of a bus, for example, and the passenger who is here sitting on the right. Excuse me for the drawing, because I'm not good at this. So let's see, this is the bus, and when bus was running, the passenger was also running at the velocity of the bus. All his body was actually at the same velocity. Suddenly, when bus applies the brake, the driver applies the brake, the portion which is the portion of the body of the passenger that is connected with the bus, right, that is in contact with the bus, will there's a frictional force, so it will be stopped, it will be braked as well, it will get stopped with the bus. But the top portion, which is not in contact, had a velocity, right, this, and it is likely to keep its velocity going, and that's why for this tendency it moves a bit forward like this. So we find our head up to this, right? So that is because of the inertia of motion. And again, the opposite thing, when the bus again starts running from rest, okay, the driver was sitting here, the passenger, okay, that was the seat, and the passenger sitting on it. So that is the top portion, that is the top portion, and that is how he was sitting. And when bus start running from rest, what happened? The portion of the passenger connected with the seat will start moving, will have the same velocity as the bus, and then the top portion, right, the top portion of the body, which is not in contact with the seat, would like to keep its original state of motion going. That means it is likely to stay rest. So the bottom portion that is gaining the velocity, but it has the tendency of keeping its original previous state. So that's why it lags behind a bit, right, like this. So it lags behind, the top portion lags behind from the bottom. So that is because of the inertia of rest. So that is the daily life happenings of this. Okay, let's see Newton's second law of motion. So what is the second law? Second law, the statement is the rate of change in momentum is proportional to the applied force. It seems a bit difficult, but let us explain, let us see what it says actually. It says, for example, there is an object, and if we apply a force on this, force F, and the mass of the object is m, and that object initially its velocity was u. So what was initial momentum? Mu, right? And if you apply force, what happened? Its velocity will change, as we have seen it, right? The velocity will start changing. So it will gain a velocity v, and the mass is same as before, so its momentum will be mv. So that is the final momentum. This is the final momentum and this is the initial momentum. So what is the change in momentum? Final momentum minus initial momentum, right? So like that is the momentum pf, right? And that is the momentum pi, in initial momentum. So pf minus, so change in momentum. Okay, if the force was applied for t second, for example, t time. So in t time, the change in momentum, change in momentum equal to pf, final momentum, minus p in initial momentum, right? And in 1 second, because our purpose is just to find the rate of change in momentum. So rate of change of anything means how much change it takes place in 1 second. So what is that? So in 1 second, the change in momentum is about what? Just you will divide this with the time. So pf minus p in divided by time. So we can write here this is equal to mv, final velocity, minus mu, initial velocity, divided by time. So that's what we find. And now, according to the Newton's law, the force applied was proportional to this. That means if we apply force, the change in momentum will be more, because the velocity change will be more, so that will result more change in momentum. So that means the force is more. If we change momentum more somehow, the resultant force, the force that's result will be more, because they are proportional according to Newton's second law. So that's how we can write F is proportional mv minus mu by t. Now let's see how we can solve it. So F is proportional. If we take m common, so b minus u by t. So we know acceleration a equal to b minus u by t, right? So we can write F is proportional m, so for this a. So that's what we can write here. Now let us promote this, how we can generate an equation from here. So let us see, make it a bit small and keep it here, right? So let's see, make it visible. Okay, so now we'll start from here, right? From here, we'll start from here. So F is, we've seen that F is proportional ma. So F equal to kma. So Newton has given k is a constant, and Newton has given the value of k is 1, and there is a condition for that. What is that condition? The k would be 1 if the force acting on it is 1 Newton. So that is how the unit of force is defined. There are unit for everything to measure. There is a meter for unit of length. There is a kg for unit of mass. So that's how there is a unit for force as well, and that unit is Newton. So 1 Newton will be if k is 1. So that means m, if you take m equal 1 kg, right? Our job is just, we have to make 1 here, means k should be equal to 1, and if k is 1, then these two has to be 1, and only then k equal 1, right? So let's see, k, and that is m1 kg, and a 1 meter per second square. So that means 1. So ultimately k is 1. So k is 1 for if 1 kg mass is given an acceleration of 1 meter per second square. The amount of force that is applied and that makes 1 kg object to raise an acceleration of 1 meter per second square. So that means what? The amount of force that you apply so that an 1 kg object develops 1 meter per second square acceleration in it. That means it develops 1 meter per second velocity in 1 second. That is 1 meter per second. Okay, if you'd like to feel 1 Newton, how much is that? Actually, you have seen 100 gram packets, right? Packets of what? You call packets of some kind of salt or other daily there are elements like what we call there are lots of packets. I can specify anyone, but 100 gram packets, right? So if you just hold a 100 gram packet in your hand, so you will find, so there's a packet that weight 100 gram, that the mass of that is 100 gram. What will happen? The weight is mg, right? So that is 100 gram times 9.8, that is gram. So convert it into kg, so 0.1 kg times 9.8, so that is 0.98 Newton, nearly 1 Newton. So if you would like to feel 1 Newton, just take 100 gram of any packet of anything, then you will feel about 1 Newton force. Now so we have we can write for a Newton F equal to ma for every Newton. So if for 5 Newtons, so just multiply it with 5. So that's the equation developed. And how can we actually use this equation to solve problems? So let's see a problems. Okay, I can give you a problem. For example, you're driving a car, right? You're driving a car on a road, and a high road, right? And that road is like hilly tracks. I mean, from the ground there is about 50 or 60 meter high road, right? So you are driving a car. Okay, you're driving a car. And that car is traveling, it's moving very fast at about 30 meter per second velocity. And for example, with the for easy calculation, let's say the mass of car is 10 kg. It's not possible, but let's say it. So then what happened? Suddenly, as you are driving, suddenly an electric pole fall on the road like this, right? So this is the electric pole. Accidentally there is a natural forces, and it drops on the road, and you have seen it instantly. And you have two options, that you cannot you cannot hit the pole anyway. So you have got two options. One is just you can apply hard brake, and if you apply hard brake, the car will stop there at this place. And or you have other option is just to let the car down to the road. I mean, let it to fall down, right? That means there will be it will roll, right? The car will start rolling like this, and you see in the movies that sometimes the car has a brake fail and then it falls down, right? So what happened scientifically in physics, there is a time difference. In both cases, the car will be in rest, and that means final velocity will be 0 for both cases, hard brake or even like if you allow it to fall. But for hard braking, the time will be less, 0.1 second. Within that, it will the velocity will be 0. But if you let it to fall, it will take much time, because if the car will keep rolling for 2 or 3 or at least 4 times to reach to the ground. So what happened? When it falls down, it takes about 6 seconds, right? So that's the difference, only time difference between these two cases. So the question is, which way is much safer for you, hard braking or letting it to fall? That's what you have to show mathematically. So momentarily you can feel, oh, if I hard brake, oh yes, with hard brake the car will be there. So if I hard brake, it's safer because the car will be there, there will be no damage to the car. Maybe I will have some kind of thirst, but it's okay, I'll manage it. But if I let it to fall, what will happen? There might be possibility of breaking hands and any bones, or even might be danger, more dangers. So that's what many of you might think, right? Okay, but how you are going to explain this mathematically? Actually, mathematically you have to show it, right? So things can be changed as well. So for example, you have to calculate here damage done. Which way, I mean hard braking or falling down, which way more damage will done. For example, if I'm hitting my hand like this, the amount of damage done, if I apply 4 to 5 times of the same of this force, there is a possibility that the hand breaks, right? So damage done depends on the force applied to it, force applied to the body. So now we'll calculate the force applied in case of hard braking and force applied to the body in case of falling. For example, we know F equal to ma, right? So as in both cases the car will be at rest, right? Car will stop. So what will happen? The final velocity v equal to 0. So so we can write m v minus u by t, right? So initial velocity is given, so minus mu by t here. So minus sign indicates that there is a braking force here, right? So there is a deceleration will take place. So now in case of hard brake, so you can write hard brake, and we'll have another case which is falling down. These two cases we'll judge with this, right? So the first case for hard brake, you see, let's avoid the minus sign because okay, keep it. So minus 10 times u is about 30 divided by 0.1, so that is about minus 3000 Newton. So if you apply hard brake, your body will experience about 3000 Newton force. So we have already talked about 1 Newton force. So if the 3000 times of that is applied, you know what happened. So you can feel it. Now falling down, in case of falling down, let us just with this F equal minus mu, right? So mu by t. So m minus m is 10, u 30. So it is same as before, just time is 6 this time, so 5. So minus 50 Newton. This see the force which is coming down to 50, the what do you call braking force, that's why it is minus. So minus 3000 and minus 50. That means the force that is applied to the body, that the body will experience is about many times less than hard braking. So that's, this way is much safer for the driver. So that is how we can judge situations based on this, right? Okay, now let's move to the next. The force that we talked about, this, right? Over one object there might be several forces working. I mean the force from this direction, force from this direction, force from this direction, but that object will have only one acceleration, this, right? So what happened here if we apply different force? That means if this is F1, if this is F2, and these are all vectors, right? So you can have vector mark. So then we'll have the summation of all these forces, and this equal ma. That is the case that when a lot of forces working in an object. For example, if you think about 3 objects, right? And there is a force applied on it. And see, there is a tension force working here between them. So the force on this object is the sum of this and this, and force on this is the sum of this and this tension force, right? So we'll have a discussion on the tension force in the later part of the the coming lectures, but I'm just showing you that the place can have more than one forces working. But you know, this object will have only, sorry, there are three objects, so acceleration will be only one. So there are three objects, right? One, m1, m2, m3. So actually it will have m1 plus m2 plus m3 m3 actually into a. So acceleration will be just one. So anyway, now the acceleration that we talked about is a uniform acceleration, and we can derive the uniform acceleration from the law of motions, like motions equations. What are those? We know v equal u plus minus at, right? We know b square equal to u square plus minus 2as. We know s equal ut plus half at square. These are the motion equation, and all the accelerations in these equations, like these are all uniform acceleration. What if there is a non-uniform acceleration applied, and how that is applied? For example, I'm showing you. In case of non-uniform a means acceleration, right? How that can be derived? For example, an equation is given, s equal 3t square plus 4t, right? 3 t cube plus 4t square plus 2. There's the equation given. And if we find the acceleration from here, what you will get? We have to derive ds by dt, right? We have to derive means there is a derivatives, differentiate it with respect to s I t, then we'll find b. So again, if we apply dv by dt, that means if we take v, this v, and again conduct dt, then we'll find acceleration. We'll find acceleration here. So let's see what it comes. Okay, I don't know whether you were familiar with the differentiation or not. So there is a basic formula of differentiation will be utilized. Let me show you. Differentiation means ddx. You'll get it in your calculus chapter. So ddx of a x to the power n. A is a constant, coefficient constant, and n also constant is a power constant. So what will happen? A will come first. There is no business with a, but n, there is a business with n. So n will come first after a. N x to the power n minus 1. That means the power of ax will come first, and then x, then power minus 1. For example, ddx of 5x square. So that is 5 will come first, and then the power of x is 2. So 2x to the power 2 minus 1. That means 10x is the result. That is how we conduct differentiation. So let us apply the differentiation here. What is that? Here, ddt, right? So ddt of 3t square. What is 3 will come first, and t square will be 3t t cube, sorry, t cube. This is t cube. So 3t square, and plus the 4, and then 2 will come first. That is 2t 2 minus 1. That means 1, and ddt of constant is 0. Differentiation of constant, like ddx of a equals 0. So with this, okay, anyway, let's see, that is this. So what is the 9t square and 8t? So again, if we apply for a, when again we conduct another derivative differentiation of b. So what happened? 9 will come first, then 2 the power will come first, and then t 2 minus 1 means 1. So plus 8, and then 1 will power 1 will come first, and then t 1 minus 1 means t to the power 0, that means 1. Anything to the power 0 is 1. So I think you will come to know it. It might seem difficult for you right now, but it will gradually be very much okay, and you will find, oh, that was so easy by that time. Okay, anyway, 18t I guess plus 8. So that is the actually, now see, that is a, right? If you see this a, if you change the time, for example 1 second, 2 second, 3 second, or 0 second, so at 0 second, if the time is 0, the acceleration was 8, because this portion becomes 0. At 1 second, the acceleration is if put 1 in t at the place of t, so 18 plus 6, 26 second. And for 3 second, for 2 second, it is about 44 seconds. So that is how 44 meter per second square. So every time, every second, the acceleration is changing, right? So that is how there is a change in terms of changing non-uniform acceleration. You have to find it like this, and then you have to find what you call force. And now let's see how can we find okay, as you were doing some advanced level thing like higher secondary level, so you will have to have more idea about Newton's second law. And what is that? For example, we have seen that the force is equal to ma, right? So we can write m a, so that is m v minus u by t. So we can write 1 by t, that is del t, right? So 1 by del t, mv minus mu, right? mv minus mu. So that is del p, means change in momentum. So like we can write d dt, d, that means in terms of change, the momentum is p, right? So we can write, sorry, you don't have to write. So d dt of mv, we can write change in momentum. That is d dt, that means change, right? Small change of this is the change in momentum. So we can write mv, d dt of mv. It was 1, right? Right now we are writing d. D means, del means change, of mv means momentum change. So let's see, we have another law of differentiation, d dx of uv. You will find it. So we can write u d dx of v plus v d dx of u. That's what. So if you look at this, we can apply it here. So we can write am comes first, then d dt of v plus b d dt of m. That's what we find it here. So let's see, here am and dv by dt, we know a equal dv by dt, right? So we can write a here, and for b, dm by dt. We can write anything here. Under normal state, as we see our surroundings, under normal condition, the am does not change. Del m is 0. Normal state, as we see, our am doesn't change. So what happened? That becomes 0. So ma remains. So that is how if equal we find ma under normal state. But you cannot avoid this, because when there are some cases where this is also come into play. Let's see where. Okay, for this we have to keep it aside. Okay, let us condense it and put it here. Now let's see how this comes into play. So force, the equation was force equal to m dv by dt plus v dm by dt. So it is normally change in velocity but mass fixed, and here change in mass but velocity fixed. So let us develop two cases. One is a plane is in the air. What happened here? The plane has a subsonic wind turbine, some turbine inside with the engine. And what happened here, this turbine give a very strong forces on the air, and air start flowing, right? Air start accelerating. Again, this turbine also develops or gives a strong force on the air, and the air start moving very fast. And what happened at this point, this will be discussed in vector division, or the chapter vector addition that happens here. So you see, at this point this force gets added, because if you draw a parallelogram, you see the diagonal, it works across the diagonal. So this is the resultant force of these two, and the reaction force of this working this way, and the plane moves ahead. So that is how plane travels. So that you can describe using this, because the velocity changes as the force is applied to air, and air makes the velocity to change, but the weight, the mass of the plane does not change. So you can develop force, you can calculate force using this equation here. But there is other case. Think about a rocket. A rocket which is traveling, where? In the space. There is no air around. So if you add the turbine here, where the turbine is giving force, here the turbine has got air to give force, but we don't have air particle here, right, around the place rocket travels. So that's why the rocket, inside the rocket there are some chambers of fuel chambers. So this is the portion where there are people, right, astronauts, but here there are nothing but the fuel, the oxygen and hydrogen they use as a fuel. And what happened, there is another chamber inside. This chamber, these both gases get mixed here, and it releases some mass. Mass means the mixture of gas is the mass of the rocket. So it changes its mass, because it throws some mass, and this change in mass is proportional to the what? This change in mass is proportional to the force, and that is how it develops a force. It gives an acceleration in the space, right? So it gives a kick to move forward. So the velocity is uniform here, because it cannot change the velocity. It can change the velocity, but through changing the mass, right? So that's how this is also useful for the special cases. And now think about a situation where both cases are applicable. We have seen two cases where one is utilized. In both cases the Newton's third law is utilized. This is the action force, and this is the reaction force, equal and opposite. So it moves, and again this is the action force. The reaction force will make the object, rocket, moving. So we'll learn about this later, because Newton's third law is about to come. So let's see now what happens. How can we explain if a case where both things are happening, like both of the equation are coming into play, like m dv by dt plus v dm by dt, both are in use. Think about a situation. For example, okay, let me put it a bit smaller, and here, right? So I hope you can see this. Now let's see. Let's say a truck, right? A truck is moving, and it carries sand or water. It either, you see in the Dhaka city, North City or South City, sometimes there are some tank, right? Petrol tank. There is a petrol carrier, and there are some water carrier, right? So what happened? They just drop water. They just fall water on the road, make the road moisture, right? Or you see that, like they let the water to absorb the heat to keep the road cool. So what happened in the truck? It's with the time, as it moves with the engine, so it accelerates, right? There is a frictional force of the wheel working with the road, and through the wheel it applies the frictional force, it applies the force to the road and make an acceleration. So that is for the engine. So this time this one comes into play. I mean this equation, first equation, this is helping, if we call this is supporting am dv by dt. So it changes its velocity through this way. And but the second case, as the water falls, what happened? The mass changing, right? The other one is v dm by dt. So this time, as water falls down, or if it is sand or anything, as it falls down, the mass changes, and as the mass the product of these two is the force. So as the mass decreases, so let me explain. As the mass decreases, so the velocity, mass into velocity is the momentum. So is the mass down, so momentum has to be up, because momentum p equal to mv. For example, p is 6. So if your mass is 6, so velocity has to be 1. So if your mass comes down to 3, so velocity has to be 2. If mass is half, then velocity doubled. If mass is 2, the velocity tripled. So that is how you have to maintain it, the momentum. So as the mass comes down, as the water falls, the velocity will increase, right? So what will happen? That increased velocity will also accelerate it, right? So it accelerates in both ways, and that develops force, that contributes to the force. Both cases, this time force is developed by both of these, right? And now what happened? If you think about in the truck, if there is a truck will accelerate, but if there is another car just front, another bus or anything at the or there is a jam always in the road. So if this happens in the road where there is a car the front, so driver cannot the truck or cannot let the truck to have accelerate, right? So this time, what if driver would like to maintain the constant velocity? What he has got to do? He has got to apply he has got to apply a force just opposite to the velocity develops. So where the velocity develops, as the mass gets down, velocity develops this side, and this way, on the on the what do you call, forward direction. So he has to, then the driver has to apply a force just opposite to the force, opposite to the developed force, because as the mass gets down, velocity increases, that develops acceleration. So that's why to stop this velocity from increasing, he has to apply a force opposite to, that is the braking force. That time the driver has to apply brake to the truck, otherwise there will be a collision. Again, what happened if there is a more water, maybe rain, there is raining heavily, and what happened, the water is falling on the open, from the opening on the reservoir. So mass increases this time. So if in case of mass increasing, what happened? As the mass increases with this rule, the velocity has to decrease, right? So velocity will come down. That means what? The track gets slower. But if there is a constant speed that the driver has to maintain, because there might be another car just behind, so it cannot get slow, right? So this time driver has to apply a force. As the velocity gets down, that means what? Acceleration takes place in this direction. So the driver has to accelerate it this way, apply a force this way, in the opposite direction, to maintain the constant speed. So that is how this thing comes into play. So you have to actually learn about this. Now think about a math. Let's see a graph. Okay, and this graph is giving an idea like this. So this is about 10, this is about 20, and this is about another 10. This is force and this is velocity. So force and velocity curve, right? And think about a mass of 5 kg, for example, or 10 kg, for example, a 10 kg mass at rest. For a 10 kg mass at rest, there is a force applied and velocity changes this way, like this graph. Find the final velocity. Find final velocity. How you are going to find it? Let's solve it. You know, here this is actually area of the mass, sorry, force and velocity. So sometimes the force is increasing, right, with the velocity increases. Again, force remains constant. Again, you see force gets down. So the force is not same always. So variable force, fixed force, again variable force applied. So we have to find it, finding the area. So if we find the area of this trapezium, this is a trapezium, right? This is A, B, C, D. The ABCD trapezium, the area of the ABCD trapezium will make you find FT actually. This is change in T, but F del T, for example. So FT or F del T equal to, we know, MV minus MU. So from FT you can find from the area of the trapezium. Area of trapezium. ABCD, right? Equal to, we know what, initial velocity as it was at rest, so initial velocity will be 0. So mv, and this is 0, minus 0. So we can find easily v from here. So v equal to, from here, v equal to area of trapezium of ABCD trapezium divided by m. So how can we find area? Area is the half. What is the parallel side? This one and this one, right? So this one, if we mark this way, if we mark this way and this way, so this 20 minus 10, so this becomes 10, this becomes 10, right? And this is also 10. So there is the height, actually that is height, this is height. So half into parallel sides, sum of the parallel sides. Parallel side, this one is how much? Oh, if give it 30, this is the 30, see. So 30 plus the other one is 10 times height. Height is here 10, this 10 equal to v divided by m. M is 10 kg. So just calculate it. This 10 and this 10 I think cut, and 30 plus 10, so 20 meter per second. That is the velocity. So that is how we can easily find problems, I mean parameters unknown from this. Okay, now think about Newton's third law. Third law is very simple, right? But there is a controversy, so let me talk about this. So third law states that every action has got equal and opposite reaction. That means if you apply a force to an object, this is object of M, right? So if you apply a force, so that is U. If you apply a force on it, that is action. This force will be in this direction, that is action. And according to Newton's third law, this object, the object M, will give the same force back to you as reaction, and that is this direction, that is reaction. And that reaction and action has to be equal and opposite. That means F equal to minus F, right? Action and reaction is equal always. Clear? And now think about this one and this one. If this the mass of this person is small, so like what happened? AM m1 m2 for example. So m1 is very greater than m2. That means what? The person's mass is very high. So very high m, this is action force and a1 equal to very small m minus m2 and a2, right? And see, as the product of them is equal as per the Newton's third law. So what happened? As the mass is very high, the acceleration will be very low, and as the mass of this is very low, its acceleration will be very high. That means if you just hit to a very small object, you see you will have nothing, but that object will have a very high speed because its mass is very low, so its acceleration will be so high. In the opposite way, if a small ball is hitting you, what will happen? The ball mass is very less and it hits you with a very high velocity. So as your mass is very high, so you will have literally no acceleration. I mean, your acceleration will be too much low, and that is the reason if a large planet hits, a small planet will always coming, or a small things is always falling to the earth, because falling earth is actually, if it hits the earth, it will jump. The earth will have no acceleration because the mass of earth is very greater than the mass of any objects we have in our surroundings. So that's why if we just throw an object to the earth's surface, it bounces up, but earth doesn't move, right? But the action and reaction was equal. The force that is exerted to the earth is exerting the same force, but that same force make this small object to bounce up again, but earth does not move because the mass of earth is too high, so it develops no acceleration. So that's why we don't see earth moving, right? Anyway, so the thing is that the action and reaction does not happen in one object. It works between two objects. That means what? It works on two objects. Actually, action, so here the action force working on object M, right? And reaction force working on the person. That means what? Action working in one object and reaction working in the another object. I am giving to the floor, I mean, I'm applying the action force to the floor equal to my weight. The floor is giving the reaction force to myself. So I and floor, myself and floor are different objects. So that's why action and reaction works on the different objects. If it would have act on the same object, what will happen? For example, this is a mass and you apply the force, this, and reaction force is also being applied to this. So action and reaction is equal, right? So what happened? This is from the opposite direction. What happened? This would have cancelled each other, right? If you add it, this would have cancelled each other. So there would have been no motion because there is no resultant force. So that's why there should not be a concept like the action and reaction force works on the same object. It always works on the different object. So that's the actually Newton's law, third law. But Newton's third law, there is application in so many, the rocket, the plane, whatever we have seen so far. You know, if you think about the rocket and plane, we talked about C. This was the action force and this was the reaction force. Again, this was the action force, this was the reaction force. And I can explain one more thing, that is, if we walk, right, what happened? How do we use action and reaction in our daily life? For example, if a person walking like this, and when we walk, we apply the action force here with an angle theta, and the reaction for the earth immediately gives the reaction force this way, and that reaction force will experience a vector division because it develops an angle with the axis, right? So it becomes r as angle with this. You will learn it in the vector division part. I have a lecture on this, so you may watch it. So r cos theta, so with this, and this will be r sin theta. So see, the reaction force gets divided into two parts, and that's how this portion, I mean vertical portion that is working up against the weight, and it will cancel out the weight of the object, but this one, this part of the reaction force will keep us moving. So that is how, using action and reaction, we are always doing whatever we see around everything almost. So that's it. That's all about the Newton's law. There are more applications. The applications of this Newton's third law is law of conservation of momentum. We will, in the coming lectures, we'd like to see this. So hope this was the first lecture we developed, so for the English medium and English version. So I hope the development of lectures for the English medium and English version will keep developing, because the other people, most of them, those who are working in this online platform, they mostly focus on the Bangla version. I am focusing on both Bangla and English version as well, so that both types of students